So myself, Gaurav Valkade. I am here to talk about the topic of transaction management and DBMS. So transactions are the core of database management systems, ensuring data integrity and reliable processing of database operations. This chapter delves into fundamental concepts of transaction management, exploring the ACID properties, resolution levels, deadlock handling, and concurrency control techniques. So let me proceed with the slides. And next slide is what is transaction. So let us understand what is transaction. First is a transaction is a sequence of database operations that must be executed as a single indivisible unit. Uh, Next is transition ensures that the database remains in valid state, moving from one consistent state to another. Next is reliable processing. Transition provide a reliable way to handle failures and maintain data integrity even in the face of systems crashes, power or outages. Next is property of transactions. So let us discuss the properties of transactions. All operations in a transaction must either complete successfully or be entirely rolled back, ensuring the transaction is treated as a single unit. Next is consistency. Transactions must preserve the database's integrity by moving it from one valid state to another. Next is isolation. Transactions must be isolated from one another, ensuring that their intermediate results are not visible to other transactions. So next we will look at transaction isolation levels. We first have read uncommitted, the lowest isolation level where transaction can see changes by other uncommitted transactions. Next is read committed. Transactions can only see changes made by other committed transactions, preventing dirty reads. Next is repeatable read. Transactions can only see changes made by other committed transactions and can repeat the same query multiple times. Next is serializable, the highest isolation level where transactions are executed in a way that is equivalent to serial execution. Next, we have to see serializable and isolation. Serial execution. Transactions are executed one after another, ensuring complete isolation and data consistency. Next is serializable schedules. Schedules that are equivalent to some serial execution, providing the same level of isolation and consistency. Next is isolation levels. Different isolation levels trade off between performance and the level of consistency in isolation. So we have deadlock detection and prevention. What is deadlock detection? It is identifying and resolving circular wait conditions where transactions are holding resource required by other transactions. Next is what is deadlock prevention? In digital prevention, we use techniques like beat type, wound wait, and timeout-based approaches to avoid deadlock situations proactively. Next is resource allocation, careful management of resource allocation and acquisition to minimize the likelihood of deadlock scenarios. We have locking protocols, like we have shared locks, allow multiple transactions to read the same data concurrently while preventing modifications. We have exclusive locks that grant a single transaction, ensuring that it can exclusively modify the log data. Next is lock granularity, the level of locking from coarse grain. This is concurrency control techniques. Acquiring releasing logs to control access to shared resources, assigning unique timestamps to transactions to determine the order of execution, assuming conflicts and rare validating transactions before commit, analyzing the dependency between transactions to ensure serializability. Next, let me summarize and take key takeaways. ECID properties transaction must be executed to atomicity, consistency, isolation, and durability to ensure data integrity. Isolation levels. Different isolation levels offer trade-offs between performance and the level of consistency in isolation. Concurrency control. Techniques like locking time snapping, optimistic concurrency, and serialization graphs ensure correct execution.